Hello and welcome again, everyone. Today we're going to talk about interpretations of probability and, in particular, subjective probability, the subjective interpretation of probability, and that will lead us to the topic of Bayesianism. If you have no idea for the moment what all these things may mean, don't worry, we'll get to everything, one thing after the other. So, last week we've seen all kinds of things about probability. In and by itself, probability, as we've introduced it and as we've discussed it last week or in the last lecture, is just a mathematical theory. This can best be seen by looking at it as a structure that is defined by a set of axioms. And this is how probability is formally treated by mathematicians. The Russian mathematician Andrei Kolmogorov formulated the decisive axioms of probability theory in 1933, and I would just like to give you a short semi-formal impression of what these axioms look like. So Kolmogorov starts from a set, some kind of set, omega. Omega is some set. This is usually called the sample space. F is a collection of subsets of omega, sometimes called the event space or a sigma algebra. F has to fulfill some conditions to qualify as a sigma algebra. In particular, it has to be closed under complement. That means that whenever any set is a member of F, the set that you get by subtracting that set from omega also has to be a member of F, and it has to be closed under intersection. That means if A and B are both members of F, then the intersection of A and B also has to be a member of F. Don't or an element of F. Don't worry about this. It won't matter much for the informal sketch I want to give you. And P is a function assigning real numbers to members of F. Then together omega F and P are called a measure space. And now Kolmogorov formulates just three axioms that place some constraints on this function P. Namely, P assigns a non-negative real number to every element of F. The P of omega of the whole set is 1. And if A and B are disjoint sets, then the union of A and B, this sign means set theoretic union, is assigned the same value as the sum of the value assigned to A plus the value assigned to B. So if P fulfills these axioms, then P is called a probability function, and omega F and P together are called a probability space. As Kolmogorov showed, given suitable definitions, everything we said last week in last week's lecture about probability is contained in these axioms. However, these axioms, they say nothing about possibilities, about knowledge, about certainty, about uncertainty, or anything of this kind. It is not even, these axioms don't say that the set of omega is in some sense to be understood as a set of possibilities or something. To make the connection to the way that we usually talk about probability, the way that we reason with probability, interpretations of these axioms are needed. And so we're going to talk about interpretations of probability theory. And first, I want to say that there are two basic kinds of interpretation. Among the various interpretations of probability theory, one distinction is particularly important. There are objective interpretations of probability theory, which conceive of probability as a measure of something that is independent of human judgment. And then there are subjective interpretations of probability theory. They see probability as a measure of conviction or confidence that something is the case. And that may very well differ from person to person. So let's look at some interpretations. What's sometimes called the classical interpretation is just the idea that probability is the ratio of the number of verifying cases to the total number of possible cases or equiprobable possible cases. They are assumed to be equiprobable cases. And this can best be explained by way of example. So take the following example. If you say that the probability of getting a 10 when rolling two dice, for example, when you play Monopoly and you play with two dice, and you get, what are the chances that you get a 10? It's 1/12, because this result occurs in 3 out of 36 possible cases. So you have two dice. Each can be 1, 2, 3, 4, 5, 6. And so there are these 36 possibilities how the sums can sum up of the two dice, and just 3 out of 36 result in 10. So this is a fairly simple idea, and something like this seems to underlie many of the earliest mathematical treatments of probability theory. That's why it's called a classical interpretation. The interpretation has some fairly obvious shortcomings or limitations, let's say. First of all, it assumes that for every statement of probability, a certain finite set of equiprobable possibilities exists. This is fine for such special cases like games with dice or card games or something, because there is a fairly clear sense of what these equiprobable possibilities are. But what does this set look like for less abstract applications? Think of, for example, the question of what's the probability that it will rain tomorrow? What is the probability that it will rain tomorrow? What is the set of equiprobable possible cases that how the weather could be tomorrow? There's simply not a clear answer to this question. So the application of this interpretation seems to be limited to a fairly narrow range of particularly simple cases. And another problem is that the possibilities are somehow assumed to be equiprobable. What does this even mean in this context, and how can we know it? I mean, on one hand, you might say equiprobability is an assertion about sameness of probability, but then, of course, it has to be the meaning of probability that is assumed there has to be itself justified on the basis of some other interpretation of probability to avoid circularity, and also because the classical interpretation obviously has nothing to say about it. Or the other alternative would be to just somehow regard the notion of equiprobability as fundamental and incapable of further justification. And this is sometimes assumed to be the case, and it's sometimes spelled out. Such an assumption is sometimes spelled out by applying a so-called principle of insufficient reason. That the reasoning goes approximately like saying that the elementary possibilities must be regarded as equally probable because we have no reason to apply an unequal probability distribution. So we have to assume that all the faces that the dice could show are equally probable because we have no particular reason to bring in any asymmetry there. However, well, this principle itself leads to new difficulties because there are often different ways to divide the world into elementary possibilities, and this can lead to contradictory conclusions. We're gonna come back to this at some point during our course of lectures, but not today. So the classical interpretation is doesn't bring us very far, but it is an objective kind of probability interpretation. Yeah, it strives to give an objective interpretation. One way to try and give an objective interpretation. Another way, another fairly traditional way to do so is the so-called frequency interpretation. It's also an objective interpretation. In the frequency interpretation, probability is interpreted as relative frequency. So under this particular interpretation, probability is primarily attributed to classes of events or types of events or properties of events. So not to singular events, but always to classes of events or types of events. Those are the things that have probability. And frequencists regard all probabilities as implicitly conditional. There's not really a frequentist idea of unconditional probability. For any probability statement, you need a reference to some basic totality, which I've here called the totality R, because you need this as a reference point. And so the probability with reference to R of Q is the probability that any given type R event is also a type Q event. That's the basic idea. The probability, and you can also then also have conditional, explicitly conditional probability statements, of course, but they are then really in the frequency interpretation always doubly conditional, once conditional on the expressly adduced condition S here, and then also always, in addition, also always conditional on the basic totality R. So this, for example, would be the probability that any given type R event is also type Q, given that it is type S. Or you could also say any given type R event that is also type S is type Q. So according to the frequentist, probability is just the ratio of numbers of events belonging to certain classes. So here the letters Q and R stand for classes of events, and the hash symbol here is really just the number of event elements in the respective class, and this sign here means it's the intersection of the classes Q and R. For example, the probability of rolling a 6 with a particular die. What's the probability of rolling a 6 with this particular die? It's just the number of all times that casting that die has resulted or will result in a 6, divided by the total number of all the times that this die has been or will be cast. Just one number divided by the other number. That's the probability. That's the rough idea of the frequency interpretation. Now you can also already see, okay, this kind of assumes that those numbers are finite, but what that can lead to problems if you include the times that this die will be cast and so on. And to avoid these kinds of problems, probability in the frequency interpretation is often defined as the limit towards which relative frequency within an infinitely growing basic totality converges. So the limit to which relative frequency converges in the long run For example, the statement that the probability of rolling a 6 is 1/6 is interpreted to mean that the share of rolls that result in a 6 converges towards 1/6 for an infinite sequence of rolls of this die. And this is then called the long-run frequency approach. The frequency interpretation also encounters some philosophical difficulties. The problem specifically for the long-run frequency approach is that there's no guarantee that the frequency we have seen so far resembles a ratio that relative frequency converges to in the long run. And this is particularly painful because the proponents of the frequency interpretation usually want to have an interpretation of probability that is open to empirical investigation, that makes probability something that is objectively that can objectively be studied by observation. Yeah, but if you turn to the long run approach, it has to be said that it actually cannot. There is really not a substantial way in which these kinds of measures are observable. And a problem for the frequency interpretation in general, not just the long run approach, is that it's also quite limited in application. There seems to be no way to assign probabilities to single events, for example, let alone for propositions that do not even describe events. For example, the probability of an eruption of Mount St. Helens within the next 20 years. What's the probability that Mount St. Helens is going to have an eruption or a major eruption? That's not a type of event. That's one particular event that's either going to happen or not. And it's not, we're not asking about how often on average does Mount St. Helens erupt in any interval of 20 years. We are asking about the next 20 years and the probability there. And it's really hard to conceive of this kind of probability in terms of relative frequency, or even things like the other example here, the probability that acrylamide causes cancer in humans. It's also acrylamide is widely considered a carcinogen, but it's not entirely it's not entirely proven. So experts would generally say that there's high probability that it is carcinogens for humans. But what does this mean in terms of relative frequency? Is it like if you have like a series of types of substances of this kind, then most of them are carcinogens or something. It just doesn't make sense. So these kinds of probabilities cannot be interpreted as relative frequencies, which limits the way that we can use this frequency interpretation. Propensity interpretation is another objective way of trying to understand probability. The propensity interpretation roughly says something like this. Probability is a quantity that describes the inclination of a system to develop towards a certain state or event, and that is predicted by the relevant theoretical laws. So this interpretation is related to the relative frequency interpretation because insofar as the relevant laws ascribe propensities to repeatable types of events, it is assumed in this interpretation that the predicted propensities will be consistent with the observed relative frequencies. But the intended advantage of this interpretation over the relative frequency interpretation is that the propensity interpretation is also able to render statements about probabilities of individual events intelligible. Um, the propensity interpretation has been proposed and discussed mainly with a view to understanding probability in quantum mechanics, where you do want to say something about the probability of one particular event occurring. These are important magnitudes in quantum mechanics, the probabilities of certain kinds of events, and they it's not satisfying, or some people have found that it's not satisfying to interpret this just on the basis of relative frequencies, because you want to say that it is a property of this particular system at this particular time to have this probability of developing into that kind of system. And that has to be a feature of this system at this particular time. And the propensity interpretation is the attempt to cache this out. There are certain limitations. I don't want to say problems, because the proponents of the propensity interpretation are clearly aware of these limitations. It has a very limited scope of application, because in most cases, we don't know any relevant theoretical laws from which we can derive the propensity of a system towards a certain state. Even in sciences that deal a lot with probability, like medicine, we do not have these kinds of theoretical laws. We don't. While we say that there's a certain probability that someone with a certain kind of condition will develop that kind of medical problem, for example, we do not have theoretical laws that specify that how large that probability is, not in the way that we have laws of particular that of precisely that kind in quantum mechanics. And second problem, even if we knew more probabilistic laws, if our knowledge of probabilistic laws was greater, it would still be, the propensity interpretation would still be inapplicable in principle to many cases where we do want to talk about probabilities. For example, the probability that a box of screws was produced by the Anton company, one of the examples that I used in the last lecture, this simply cannot be understood as a theoretically determined inclination of a system, because it's a probability about something that has already occurred, and either has occurred or has not occurred, but still we want to talk about these kinds of things in probabilistic terms, and there's no way that this could be understood as some kind of inclination or propensity of system to develop in a certain kind of way. So that was a sketch of a number of attempts to cache out what probability is in objective terms. And I just explained these to cover the ground a little bit and prepare you for the subjective interpretation, hopefully having motivated you a little bit that another kind of interpretation is needed, and all we have encountered so many limitations with these objective interpretations. So perhaps you are at least willing to consider interpreting probability subjectively now. So what's the idea? In the subjective interpretation, just says probabilities are degrees of belief. They are personal degrees of belief. Well, it is arguably quite plausible that belief comes in degrees. For example, I believe that the sun will rise tomorrow, and I also believe that I will not have a beer in the pub for the rest of this semester. I believe both of these things, but I don't believe them to the same degree. I very, very strongly believe that the sun will rise tomorrow. And I also kind of believe that I won't have a beer in a pub for the rest of the semester. But to a lesser degree. But I do believe that, but to a lesser degree. So the subjective interpretation of probability is simply that probabilities can be understood as a measure of this phenomenon, a measure of degrees of belief. So what I just said is cashed out that I think it very probable that the sun will rise tomorrow, and I think it also very probable, but not as probable, that I will not have a beer in a pub for the rest of the semester. So how do we get from the plausible idea that degrees come in beliefs to a mathematical function that assigns numbers between 0 and 1 to any belief? That seems quite a step. And the considerable success that subjective interpretations of probability have had in the 20th century is connected to one very intuitive operationalization of degrees of belief that was developed in the early 20th century, namely associating degrees of belief with willingness to bet. So, some terminology first. A price for a bet that pays €1 if proposition A is true and pays nothing if A is false is considered fair by a subject if and only if this subject is willing to sell this bet for any amount greater than this price and is willing to buy it for any amount smaller than this price. So we're considering some very basic, simple kinds of bets, where you pay a price for the privilege to take part in the bet, and then the bet is about one particular proposition, and if that proposition turns out to be true, you get €1, and if it turns out to be false, you get nothing. The seller of the bet keeps the price you've paid in any case. So as a buyer of the bet, what you gain is the difference between €1 and what you've paid for the bet. And so the question is, on which conditions will you be willing to sell these kinds of bets? So act as the person who will give the €1 as a reward if the proposition turns out to be true. Or buy the bet, that is, pay someone the price in return for the promise that they will give you €1 when the proposition turns out to be true. So the idea now is that someone's degrees of belief, as is now some subject, can be measured by what prices of bets S considers fair. So if S considers 65 cents a fair price, then we'll say that their degree of belief in that particular proposition is 0.65. For example, Alice thinks that 35 cents is a fair price for a €1 bet that Germany will win the next World Cup. And the following lines are just cash out what this means. This means that she's willing to pay, for example, 34 cents to Berit in return for Berit's promise to give her €1 if Germany wins. She would also be willing to pay 33 cents or any amount lower than 35 cents. Yeah. And Alice is also willing to take 36 cents for Carmen and in return promise to pay her €1 if Germany wins, because she thinks like, well, that's fair for me as a seller because it's kind of 35 cents is exactly the fair price, so I'm happy to sell the bet for a higher price. And if this is in fact so, we say that Alice's degree of belief in the proposition that Germany will win the next World Cup is 0.35. Now, note that there is probably a fairly unrealistic assumption underlying this whole conception, because real people are risk averse. They avoid risk to different degrees. I mean, not all people are risk averse in the same amount, but they are all risk averse to some degree. And what that means is that there will typically be a gap between the prices at which they will be willing to sell the bet and the prices at which they are willing to buy a bet. And this definition kind of assumes that they meet in exactly in one point, and that point is the degree of belief. That is, if you will, an idealization that we undertake in conceptualizing and operationalizing degrees of belief in this way. There have been some proposals how to deal with this problem. David Christensen, for example, in 1996, proposed that we should talk about the degree of belief that justifies the subject in deeming a bet favorable, whether or not S would actually be willing to pay or sell the bet. It's Christensen says we should talk about what they feel justified or are justified in deeming a favorable bet, and then allowing for the possibility that they may deem something a favorable bet, but still not be practically willing to buy or sell the bet at the according prices. So, be that as it may, I've informed you of this theoretical problem, or of this element of idealization that clearly is underlying this kind of conception. But so, be that as it may, this operationalization explains how you can reasonably assign numbers to degrees of belief. But maybe it does not yet obviously, in any obvious way, explain why these numbers that you assign to degrees of beliefs are probabilities, are probability measure. So is there any reason why degrees of beliefs understood as willingness to bet should conform to the mathematical laws that follow from Kolmogorov's axioms? Yes, there is. Proponents of the subjective interpretation think there is, and this is actually an important part of the interpretation. So you should consider this proposition as really belonging to the subjective interpretation. A rational agent's degrees of belief must conform to the mathematical laws of probability. Or put it other way, if a subject's degrees of belief don't conform to the mathematical laws of probability, they are not rational. In the early 20th century, two theorists devised a very clever argument to show why this must be so. And this argument is called the Dutch book argument. The main content of the Dutch book argument is as follows. If a subject S's degrees of belief do not conform to Kolmogorov's axioms, and S is willing to buy and sell bets for prices she considers fair according to her degrees of belief, then there is a finite combination of bets that S will be willing to accept and that guarantees that S will lose money. This is called a Dutch book, this kind of combination of bets. And this claim here is something that is provable. The reverse is also provable. If S's degrees of belief do conform to the axioms, no Dutch book against her is possible. And so this thing has been proven. There are two classical papers, one by Frank Ramsay from 1926 and one by Bruno De Finetti from 1937, where the Dutch book argument is articulated and proven. I will not rehearse the proof here, but I will illustrate and make it, try to make it plausible and understandable what this means. So take this very simple example of Otto. Otto has degrees of belief that don't conform to the laws of probability, because Otto thinks that there is a 5% probability that it will rain tomorrow, and being sort of an optimistic spirit, he also believes that there's a 99% probability that it won't rain tomorrow. So this, as you know, does not conform to probability theory, because the probability of negation has to add up to 1 with the probability of the original statement. And now, if Otto has these kinds of subjective probabilities and he's willing to buy and sell bets in accordance with his subjective probability judgments, then he should be willing to buy the following bets, namely number one, a 100 euro bet that it will rain tomorrow for the price of 4 euro, because he thinks that there's actually a 5% probability, so he would pay up to 5 euros, but so he'll happily buy the bet for 4. And also a 100 euro bet that will not rain tomorrow for the price of 98 euro. This is because of his second belief. Yeah, he thinks there's a 99% probability, so he considers 99 euros a fair price, and he's happy to pay a little less even for this nice bet. Obviously, if he buys both bets at once, he will always get 100 euro, because if it rains, he gets 100 euro from his first bet. If it doesn't rain, he gets 100 euro for a second bet. So he always comes out 100 euro, but he has paid 102 euros for both bets together. So he will always come out 2 euros short in the end. So he loses money come what may. This combination is called a Dutch book. And so this was a fairly obvious example. I'm going to give another illustration to sort of give you the sense that you can always, in case of any inconsistency, you can always construct this kind of thing. By the way, I've upped the stakes a little bit from 1 euro to 100 euros, because it makes it easier to really think of this as a problem for Otto, yeah, or for Heinz, as may be the case. Heinz thinks that there's a 20% probability that France wins the next World Cup, 20% probability that Italy wins the next World Cup, and a 50% probability that France or Italy wins the next World Cup. As you know, it shouldn't be like that, because to stay consistent, he should assign a 40% probability that France or Italy wins the next World Cup. Whatever you think about these numbers, how realistic or how they conform to your own estimations of these probabilities, that's not the point. The point is in the internal consistency of these three probability assignments, and there's an inconsistency there. And the Dutch book argument tells you exactly how this inconsistency is irrational. Because if you have these kinds of probability assignments and you act in accordance with them, it is possible to put you in a position where you will lose come what may. And that's irrational, to allow yourself to be put in that position. It's okay to lose sometimes and to win sometimes, of course. Yeah, we cannot avoid this because we are not omniscient and whatever. But it's not okay to have a set of beliefs that will put you in a position that you will lose come what may. And so here is the idea, or here's how it works out for Heinz. He will be willing to sell a 100 euro bet that France wins for 21 euro. So he's now selling the bet. He's giving, say, Alice. He's taking 21 euros for Alice and gives Alice the promise that she will get 100 euro if France wins. He also, at the same time, sells a 100 euro bet that Italy wins for 21 euro. He would also sell it for 20 euros 50, but okay. Alice gives him 21 euro, and he happily takes it. And also because of his third belief, he should be willing to buy a 100 euro bet that Italy or France wins for 49 euros. And in the combination, this is how it works out. If France wins, he has to pay 100 euro to Alice, but he gets 100 euro from his third bet. If Italy wins, he has to pay 100 euro for the second bet. He has to pay out the 100 euro for his second bet, but he will also get 100 euro for the third bet he bought. And if neither France nor Italy wins, he won't get any payouts, but he also won't have to pay out any payouts for any of the bets that he sold. So he will always come out even from the bets, but he has paid altogether minus 7 euros. So he got 42 euros for the bets he sold, but he bought a bet for 49 euros. So he has already bought 7 euros for a combination of bets that is guaranteed to give him 0 in return. So now, as I said, the idea of the Dutch book theorem, and it's not just an idea, but there's an actual mathematical proof, is that you can prove that this is always the case in any kind of inconsistency or incoherence in the sense of degrees of belief that do not conform to the laws of probability. There is this kind of Dutch book that you can construct. So you can actually prove mathematically, and also the other way around. As I said, if you do conform to the Kolmogorov axioms, this kind of thing cannot happen to you. The Dutch book theorem is the most famous argument in favor of the claim that a quantitative measure of degrees of belief ought to take the form of a probability function. It is not the only such argument that is available. Another way to argue for the same conclusion is by way of so-called representation theorems. Representation theorems is what we call a kind of strategy where you start from a number of constraints that a mathematical function has to fulfill in order to count as representing a particular kind of property or relation. So you number certain constraints. And then you go on to construct a proof that only one particular mathematical function satisfies all these constraints. Or, as is more often the case, that every function that satisfies all these constraints is isomorphic to a particular mathematical function. And several representation theorems of this sort that aim to show that degrees of belief ought to be represented by a probability function or a function that is isomorphic to a probability function have been constructed over the years. Arguably, even Ramsey's 1926 paper contains the sketch of a representation theorem to support this claim as well as an early version of the Dutch book theorem. And different kinds of representation theorem supporting probabilism for degrees of belief are helpfully reviewed in the first chapter of Sprenger and Hartmann's book, Bayesian Philosophy of Science. But I will not go into the details of any of them. I will stick with the most. I will rest content with having sort of hopefully plausibilized the Dutch book theorem for you as a way of understanding what's the connection between degrees of belief and probabilities. So, in the philosophy of science, the idea that one should use subjective probability to model and study scientific inference is the core idea of the school called Bayesianism. It's the core idea, but it's not yet the full school of thought. In addition to representing degrees of belief by means of a probability function, apologies, we need another core idea to understand Bayesian philosophy of science. What we said so far allows us to identify constraints on how a subject's degrees of belief are allowed to be distributed over a range of propositions at any given time in order to count as coherent or rational. But clearly, the degrees of belief of a rational agent also change over time. In particular, they change in response to learning new evidence. Whatever my degrees of belief is now that Germany will be the winner in the 2022 Men's Soccer World Cup, and whatever happens in 2022, my degree of belief will change in response to it. And so should yours. I just realized that the possible exception is maybe if you are already certain that it is true or certain that it is false, then events may develop in such a way that you do not need to change your degrees of belief. But under the plausible assumption that your degree is neither 1 nor 0, your degrees of belief will change during the course of the year 2022. So Bayesians have a normative idea on how changes in degrees of belief ought to come to pass. So there's not only constraints about how degrees of belief should be distributed over your range of beliefs at any given time, but there is also a constraint on how you should change your degrees of belief in response to learning new evidence. And this is articulated in the so-called rule of conditionalization. The Bayesian conditionalization rule comes in variants, but I will start by just introducing the basic variant of the conditionalization rule. So, the Bayesian idea of conditionalization is the following. Basic learning events trigger updates to a subject's degrees of belief. So degrees of belief change in response to some events, learning events, when you learn new evidence, for example. And if A is the strongest proposition that is learned, the updated distribution of degrees of belief, think of this as a new kind of probability function. This is a probability function as well, but it's a new distribution. It also has to fulfill the Kolmogorov axioms and so on with internally for the new state of your mind. Yeah. This is generated from the old probability distribution, which is also a distribution that in and by itself satisfies Kolmogorov's axioms. And generating the new probability function from the old is done by following this rule. For any proposition X, the probability, the new probability of X, the new unconditional probability of X is the old conditional probability of X given A. So if you learn that Germany will be in a group with Brazil and Italy and the Netherlands, that's the new kind of information you get, then you should update your subjective degree of belief that Germany will be the winner of the next World Cup to what used to be your conditional degree of belief that Germany would win, given that they are in a group with Brazil, what did I say, Italy, and the Netherlands. So if in practice, when we want to use this, we almost always need Bayes' theorem to calculate what this means. And therefore, often the rule of conditionalization is immediately written like this. And also, we don't write X and A because typically what we're interested in, especially in philosophy of science, is some kind of hypothesis. And the kind of the A that triggers the update, the strongest thing that you learn is typically some piece of evidence. And that's why we usually use E for that thing, that proposition that is learned, and spelled out with the aid of Bayes' theorem. The conditionalization rule looks like this, and if you spell it out like this, it's often also called Bayes' rule. Yeah. I would also like to introduce some useful terminology here. So this here, the new kind of unconditional probability of H is called the posterior probability, and the old unconditional probability of H is called the prior probability, or short, the prior. And these things here, the probability of the evidence given the hypothesis, that's sort of a measure of the degree with which the hypothesis predicted the evidence. Yeah. For example, if the hypothesis really straightforwardly predicts the evidence and says, as a logical conclusion, basically, this is one. Yeah, this would be one. But usually it's a little weaker. In any case, this kind of probability is called the likelihood. It's a little annoying, this terminology, because usually really just in English, likelihood just means the same as probability. But when we talk Bayesianism, then likelihood always means a particular kind of probability, namely the conditional probability of the evidence given the hypothesis. So note that while Bayes' theorem, so this part of this equation, this equation here, Bayes' theorem is just a theorem that follows from the axioms of definitions of probability of probability theory, and you have to accept Bayes' theorem whether you are Bayesian or not, and whether you do subjective or objective or frequency interpretation or whatever. Bayes' theorem holds, but this whole thing, this part of the equation, that this is the way you update your degrees of belief, that is not a theorem of a probability theory. That is a main tenet of the school of Bayesianism. So Bayes' rule is not the same as Bayes' theorem. By the way, the Reverend Thomas Bayes lived from 1701 to 1761, and he was an English mathematician and Presbyterian minister who used and proved a special case of Bayes' theorem in an essay that was posthumously published in 1763. Bayes himself did not advance a subjective interpretation of probability, so Bayes himself is not the first Bayesian or whatever. But the essay that he wrote touches upon the problem of rationally updating probability estimates. And so the name Bayesianism is not entirely inapt for this school of thought. The name has somehow stuck. It's probably not the best or most informative name that could have been used. So what is Bayesianism? We can sum up, so the main tenets of Bayesianism are nicely summed up in this new book by Jan Sprenger and Stefan Hartmann, Bayesian Philosophy of Science, and they analyze the following three ideas as the main tenets of Bayesianism. First, there's a static dimension, which they also call probabilism, and that's just that the degrees of belief of a rational agent are represented by probability functions. So that which is, for example, I mean, you can motivate that by means of Dutch book theorem and so on. Then there's a dynamic dimension, namely Bayesian conditionalization or some generalization thereof dictates how a rational agent should revise her degrees of belief. And there's also a practical dimension, namely the posterior probability distribution is, together with an agent's subjective utility function, the rational basis for assessing evidence, accepting hypotheses, and making decisions. So Bayesianism has a strong normative content that subjective probability contains the key to understanding rationality and contains the key to what ought to be the basis of these kinds of epistemic decisions, epistemic choices, but also some choices that go over and above the realm of the epistemic. So what Sprenger and Hartmann call orthodox subjective Bayesianism is the doctrine that these three dimensions sum up everything that one can and must demand of rational degrees of belief. In particular, orthodox subjective Bayesianism places constraints on the internal coherence of a subject's degrees of belief and on how they must be updated in response to learning events, but they place these orthodox subjective Bayesians place no constraints on prior probabilities. Prior probabilities will come from somewhere, and as long as the agent has, for as long as the agent has been a rational individual, they must reflect a history of Bayesian updating. But other than that, the orthodox subjective Bayesian makes no claims about where prior probabilities ought to be taken off or what they could be, this orthodox position is by now a minority view among Bayesians. So it's orthodox in the sense of that it was the original view. Richard Jeffrey is a theorist that is particularly associated with this take on Bayesianism. But most Bayesians now would add another constraint that tempers the subjective nature of the Bayesian view on rationality somewhat. And this additional principle is often called the principal principle. Note the different spelling of this principle and this principle. The name principal principle was goes back to David Lewis. And the idea is the following. Wherever a rational agent has some knowledge of objective chances, that is, relative frequencies, propensities, and so on, her degrees of belief should conform to the known chances. For example, if you know that the half-life of the iodine isotope iodine 131 is 8 days, then your degree of belief that this iodine 131 atom will decay within the next 8 days ought to be 0.5 if you are rational. No? And so the orthodox subjective Bayesian would not make such constraints. She would say, oh, you should just have those kinds of degrees of beliefs that are consistent with your history of Bayesian updating of your beliefs, and that's all. But this view that is fairly standard and that Sprenger and Hartmann call tempered or calibrated subjectivism or Bayesian personalism. This view would say that you ought to take objective chances into account wherever you can. So calibrated subjectivism asserts that we sometimes, in the case of some propositions, have the opportunity to take our knowledge of objective chances into account and take clues from how to assign prior probabilities from what we know about objective chances. And in those cases where we have this opportunity, we ought to use it also in order to be fully rational. That's now kind of a mainstream view. There's also a radically different version of Bayesianism called objective Bayesianism. And objective Bayesian thinks that there is always one privileged degree of belief, so that there's always one right way to assign priors. But for the start, I shall ignore objective Bayesianism and go with the more standard versions that I have introduced on this slide. So next week, we're going to have a look at some of the things that Bayesians have to say about scientific inference, and in particular, we're going to concentrate on Bayesian confirmation theory. So see you then.